For this video, I want to go through an example of an application problem involving systems of linear equations, and I want to use a different technique called Cramer's rule. Cramer's rule is in our text in section 5.4, and I've taken these screenshots from our text in that location. It does require that our systems of equations be in this standard form. And the really cool thing about it is that we can get directly, almost immediately, a solution for x and y using something called determinants. Notice that these determinants are the coefficients or constants from this standard form. You can read more about determinants from our text, and I will also show you how to use determinants through this example with Cramer's rule. There are some key features to note about Cramer's rule. The determinants in the denominators are the same. They are formed by using the coefficients of x and y. So really you only have to find or evaluate this determinant once, and you know it's the same thing for y, or vice versa. In the solution for x, the determinant in the numerator is obtained from the denominator determinant by replacing the x coefficients with the constant terms. So instead of a1, b1, a2, b2, these x coefficients are replaced with these c constants. It's now c1, b1, c2, b2, as you see right here. And something similar happens for y. Its determinant is formed or obtained by replacing the y coefficients with the constants. Those y coefficients were b's, and notice now they are being replaced with constants, c's. All right, let's look at that example. For this example, our first step is to develop the two equations and two unknowns. So in that way, it's a little bit different, more of an application type problem. We're told sterling silver is 92.5% silver and 7.5% copper. One silver copper alloy is 94% silver, and a second silver copper alloy is 85% silver. How much of each should be used in order to make 100 grams of sterling silver? I really like the way that this chart helps format or organize rather all of our information. So notice that along the columns here we have headings like amount of the mixture, the percent of the ingredient, percent of silver, and the amount of the ingredient of silver. Okay, and along the rows we have these labels: the mix 1 for alloy 1, mix 2, and the final mix that's supposed to be 95.5% silver. Let's see how the problem and the information within the problem rather can be used to fill in this chart. So mix 1 or alloy 1 had 94% silver. Mix 2 had 85% silver. And the final mix for sterling silver should be 92.5%. Next, we're asked how much of each should be used. So we can safely assume here these may be different amounts. Let's label them x and y. These are our unknowns. We want that to make altogether 100 grams of silver. Sterling silver to be exact. So that's that final mix needs to be 100 grams. Change your percents to decimals. Multiply the amount times the percent to get the amount of the ingredient, or in other words, the amount of silver. So we get x times 0.94 is x times 0.94, or 0.94x, however you may want to write that. And each of those are being calculated through the rows. Now what we can do is write our two equations. So if we look down through this second column here, we have the amount of silver should be a total of 100. As an equation, that means x plus y equals 100. Similarly, when we total the amount of the ingredient, it should equal this constant. So the second equation is formed as such. X times 0.94 plus y times 0.85 equals whatever 100 times 0.925. Now let's use Cramer's rule to solve for x and y. Make sure that you are first writing your linear equations in standard form, which ours were really close to that already. The only thing, notice, that's a little bit different from that last slide is the 0.94 is now in front of the x, just to make it a little bit more clear that it is its coefficient. And we have calculated this constant c for that second equation. On the same thing for y, we did move the 0.85 in front of y. Let's next form these determinants by grabbing the coefficients of x and y. The coefficient, if you do not see it, is understood to be 1. So a sub 1, in other words, is 1. B sub 1 is 1. 0.94 goes here. 0.85 goes here. That is only one of 3 determinants that we will have to calculate. The next one, we will replace x, or the x coefficients, with the c's, the constants. We will now write this new determinant, and we'll use that in a minute to get our x value. But notice that instead of using the 1 and the 0.94, they are being replaced with the constants, 192.5. Next, we're going to replace y with the c's. So again, think back to your original where you had x and y coefficients. These y coefficients, 1 and 0.85, are now being replaced with 192.5. Next, we evaluate these determinants. Now, I didn't speak to this earlier in the first slide, but you have already read about it, I'm sure, from section 5.4. To evaluate a determinant, you multiply through these diagonals and subtract those products. Specifically, you multiply through in this way. 1 times 0.85 minus 0.94 times 1. That gives us a value for that first determinant of negative 0.09. Do the same process for the other two. Notice these values, that this next one should be negative 7.5. The last one is negative 1.5. And then apply Cramer's rule. So Cramer's rule says that x equals that determinant where the x's were replaced with the c's. Remember that one? That was the negative 7.5. Divide that by the determinant that was using the coefficients of x and y, which is the negative 0.09. Y is something similar, but it's definitely the same for the denominator, but the numerator is the only thing different. Its y values are replaced with the c's. That's this determinant divided by negative 0.09. Immediately, you have the values for x and y. What this means in the context is that x equals 83.3 grams of the 94% silver alloy, and y equals 16.7 grams of the 85% silver alloy.